Okay, let me start. Today we are going to talk about the subspaces. Okay, where are we now? Before starting, let's go back to our lectures 4.3. Actually, the lecture 4.3 was the end of the chapter 1, right? So where are we now? So we are here. So actually, this is the chapter 2 in our textbook. So it means that today's lecture is the end of the chapter 2. It means that there will be another homework of the chapter 2. So let's see what is the homework 2. Anyway, so after this week, we will finish the chapter 2, right? In chapter 2, we've talked about the matrix operation and matrix inverses and LU factorization, something like that. And what was the LU factorization in the last lecture, in the last week lecture? We can decompose the arbitrary matrix A into the matrix L and matrix U, right? So why we need the LU factorization or LU decomposition? We want to solve the AX equals B, right? So from whole this course, we are interested in solving the AX equals B or AX equals 0 or AX, yeah, until now, yeah, AX equals B and AX equals 0, right? So by introducing the LU factorization based on some kinds of the matrix operation, then we can accelerate the solving the solution, right? Because the LU factorization based method is much easier to solve than the original AX equals B. Okay, so this is why we introduced the LU factorization. Today we will introduce a new concept, subspaces or basis. And in this third day, we will introduce the dimension and length property. Okay, okay. Let's start today's lecture. Okay, so first of all, what is the subspace? What is a subspace? The subspace of Rn space is any set H in Rn space that satisfy three following property. Okay, so let's say there is the Rn vector space, right? And then there is the subset, let's say H in Rn space. Then if this subset H satisfy three following property, then we can say that this subset H is the subspace. Okay? Okay, so first of all, the first property is the zero vector is in this subset H. What does it mean? If the zero vector is in this H, this subset H, then this first property is satisfied. Okay? The second property is that for any vector u and v in H space and subspace A, then some u plus H is in subset H. What does it mean? Let's say vector u and vector v in H space, then vector u. So to any subset any subset of H is a subspace when this relationship is satisfied. So this is the second property. The third property is that for any vector u in H space and each scalar c, then the vector c times u is in H space. So vector u H space and c is just a scalar value, then c times vector u is also H. Okay, so every subspace satisfy every subspace must satisfy these three following property. Okay? So this is the condition of the subspace. In other words, the subspace is closed under addition, right here. Then closed under scalar multiplication, as you can see here. Okay, so this is the definition of the subspace. Then, okay, let's see the examples of subspace. If the vector v1 and v2 are in Rn space, let's think about that. Think like that. Okay, Rn space are here, and there is a two vector v1 through the v2, right? Then H is the span of the v1 and v2. Okay, then we can find out the span v1 and v2. By the way, what is the span? Span means the linear combination of the v1 and v2, right? With the scalar value, right? Then this H space, the span of the v1 and v2 is the subspace of Rm space. Okay. Let's prove the span of the vector v1 and v2 is the subspace. How can we prove? We have to check these three property. Okay, let's check the first property. The zero vector u is in H, or span of v1 and v2. Why? The zero vector is the 0 times v1 plus 0 times v2. So this is the one sample in the span v1 and v2, right? So it means that zero vector is in the span v1 and v2, right? Okay. The first property is satisfied. Okay, let's check the second property. To verify the second property, let's take two arbitrary vector in U is equal to h1 plus h1 v1 plus s1 times v1 plus s2 times v2. Okay, so in this case, s1 and s2 are scalar value, right? Then let's say v is equal to something like that, t1 times v1 plus t2 times v2. Okay, so to check u plus v in space H, let's compute the u plus v. So by a property of the vector operation, u plus v can be represented something like that. S1 plus v, t1 times v1 plus s2 times s2 plus t2 times v2, right? So this is also scalar value, right? Scalar values. So it means that u plus v is a linear combination of v1 and v2, right? So u plus v in H space or span v1, v2, right? From here, right? Okay, the second property is satisfied. Okay. For last one, for any scalar c, value c, the vector c times u is in H space. Why? The c times u is equal to c times s1 times v1 plus s2 times v2. Then we can represent c s1 v1 plus c s2 v2 because cs1 and cs2 is the scalar value, right? Scalar values or real values. Then And we can say that C times U is the linear combination of the V1 and V2. So the third property is also satisfied. Okay, so from here we can say that the span of the vector V1 and V2 is the subspace of the Rn space. Okay, so this is one example of the subspace. Okay, so let's see the visualization. Okay, let's say we have the vector v1 and v2 in R3 space, on R3 space, right? Then what is the span of the v1 and v2? This one, because the linear combination of the v1 and v2, right? So this is the plane in the R3 space, right? Then this plane is the subspace, right? So it means that the zero vector contained on this plane and the summation of the vector v1 and v2 is also in this plane, right? Then another vector, let's say 3v2, okay? 3v2, this vector is also in this plane, okay? So these three properties are satisfied, so this span space is the subspace, okay? So this is one example of the subspace. Okay, actually we can generalize this example to the V1 through the Vp case. Any number of the vectors. Okay, let's generalize that. Okay, for vector 1 through the vector p in Rn space, the set of all linear combination of the set of the all linear combination of the V1 through the Vp. So in this case, it's like x1 v1 plus x2 v2 plus xp vp. So this is the linear combination of the vector 1 through the vector p. Okay, so actually this is the span v1 v2 vp, right? So this linear combination of the vector v1 and v1 through the vp, or span of v1 through the vp, is the subspace of Rn space. Okay, why? You can prove this statement similar to this one. Okay, the only difference is that in this case we only consider the two vectors, but if we have the arbitrary number of the vector, but we can do similar things here, right? On summation and multiplication. Okay, so please do it yourself. Okay, anyway, the span or linear combination is a subspace. Okay, so by the way, from now on, the span v1 through the vp can be represent the subspace span or generated by v1 through the vp. If you remember the definition of the span in our last lecture, there's no terminology like the subspace, but now we know what is the subspace, so we can say that the span v1 through the vp is the subspace spanned by v1 through the vp. Okay, so this is a very important statement. So by using this, we will prove the our next subspace is the real subspace or not. Okay. Before that, let's see another subspace. And let's see another examples of the subspaces. So first of all, a line a line L not through the origin, for example, like this one, right? It's not a subspace. Why? Why? First of all, because it does not contain the origin. Why? Because origin is here, but the line is not through the origin, right? So the first property is not satisfied, and the L is not closed under addition and scalar multiplication. For example, the vector u and v on the line L and the vector u plus v here, right? It's not on the line L. So it's not satisfied. This is not satisfying the second property, right? Another property is that the vector w and the scalar multiplication of the w is the 2w, right? But this vector is not on the line L. Okay, so here and here, so we can conclude that the line L not through the origin is not a subspace. Okay. Another example here, the Rn space itself. Rn space is also subspace. Why? Because they satisfy the three property. What was that? Okay, the zero vector is in the Rn space, right? And vector u and v in Rn space satisfying vector u plus vector v Rn space, right? And u Rn space and c scalar, then c times u still in Rn space. So this Rn space is the subspace. Okay, and the set containing only the zero vector in Rn space is called the zero subspace. Why? Then to prove that, we can check this zero vector is satisfy the three property. Okay, the veritable. Okay, let's say the zero vector is h, then zero subspace is h, then zero vector itself in h space, right? Then zero vector is also zero vector, so this is in space h, right? Then c times zero vector is also zero vector, so this is also h. Okay, so this is the proof of the zero vector. The set containing only zero vector in Rn space is called the zero subspace. Okay. Okay. Oh, by the way, do you know what is the zero vector in Rn space? Right. The zero vector means like 0, 0, 0, 0, 0, and number of the zero is the n. Okay. This is the zero vector. Okay. So this is the examples of the subspace. Okay. Okay, here is the example. Let the vector w be the set of the all possible vectors of the form like this. Then show that vector w is the subspace. Okay. Okay, so first of all, let's decompose this original vector in terms of the vector value a, b, c. How can we do that? Extract the a from the term related to the value a. So here, here, here. So here is the remaining vector like that. And if we extract the vector b, then here, the vector like that. And if we extract the c here, the remaining vectors are like this. Okay, then what is this one? this is the linear combination of the vector, this one, and this one. Or this is the span of the this one, okay? Okay, because this vector W is the span of the arbitrary vector, right? So because the vector W is the span of the three vectors, so the vector W is the subspace, okay? From this statement, okay? Okay, so so far we've talked about what is the subspace. Then from now on we will introduce the two representative subspace, the column space and null space. Okay, let's start from the column space. What is the column space? The column space of the matrix A is the set of the whole linear combination of the columns of the matrix A. What does it mean? Okay, let's say that we have a matrix A, something like this, then it consisting of the column vector A1, AN, right? Right. Then what is the linear combination of the column vectors, columns of the A or column vectors of the A? This is just the span, right? A1 through the AN, right? Then the column space of the matrix A is this one, right? So we can call the column space of A is the core A. Okay, so yeah, here's the definition. Yeah, so okay, if the matrix A is something like that, and let's say the size of the matrix A is n by n, then the size of the column vector is the what? Rm space, right? And number of column is the n, right? Then column vector, column space A is the same as the span A1 through the AN, right? So, in other words, the column space A is the span A1 through the AN. Okay. Okay, so this is the definition of the column space. Then, in other words, the column space of the n by n matrix is the subspace of the Rm space. Why? Because the column space is the spans of the column vector here. So it means that this is the subspace of the Rm space. Why? From this one. Okay? Okay, so we know that the column space is also subspace. Okay. Then there's another statement. The column space A is equal to Rm space when the columns of A span the Rm space. So what does it mean? The columns of the A span the Rm. What does it mean? What's the definition of the span? x1 a1 plus x2 a2 plus xn an, right? Then let's say there is the vector b of the column space, the linear combination of the column vector a, right? Then what is that? This is ax equal b, right? Right? So the columns of the matrix A span Rm means, okay, this is the solution space and this is the output space, right? Then let's say there is a mapping with the matrix A, right? So we can think this is the vector B and this is the solution X, okay? Then the columns of A span mean every possible B with the X is the same with the RM spaces of, okay? So in this case, the column space equal to RM space. The column space, the span of the column vector A is equal to RM space. Otherwise, if there is the RM space here and the possible vector B here, and there is some point that doesn't have the solution, something like that, then in this case, the column space A is only part of the RM. So the column space A is the part of the RM, okay? Okay, so this is the property of the column space. Okay, so let's see the example. Okay, let's say the matrix A is something like that, and vector B is something like that, and determine whether vector B is in the column space of the matrix A. Okay. So, first of all, this is the column vector A1, A2, A3, right? How can we determine whether vector B is in column space of A? First of all, what is the column space? The column space is the linear combination of the column vector, right? So this is the x3, a3, right? Then if we put the p here, put the p here, then if there is the values x1, x2, and x3 that satisfy this statement, then we can say that vector B is the linear combination of the column space, column vectors, or the column space of A, right? So the problem is there is the solution or not of this statement, right? So this statement can be rewritten like that: Ax equals B. Okay. So in other words, the problem is the Ax equals B has a solution or not. Okay. So this is the problem of this example. Okay. So okay, let's solve this. The solution. In the solution, the vector B is the linear combination of the column A if and only if the vector B can be written as Ax, or Ax equals B has a solution. So, in other words, the linear combination of the matrix A is equivalent to the Ax equals B has a solution or not. Okay, so so far in this course we've talked about how can we solve the Ax equals B, and where we can check there is a solution or not. If there is a solution, the solution is unique or not, right? So we already know how to do that. Okay, so first of all, we have to set the augmented matrix AB, right? And then we have to row reduce this matrix to the echelon form, or reduce the echelon form. Okay, so first of all, this is matrix A, this is vector B, right? Then how can we do that? First of all, we have to remove this one from this row, right? Like that. We already know this, right? Then this is 0. Then what about next? We have to remove this one from this one. Okay, so this is the echelon form. Okay, so we can further low reduce this echelon form into the reduced echelon form, right? Something like blah 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 this, right? But to check there is a solution or not, the echelon form is enough, right? So from here, there's no row like 0, 0, 0, 0, b, where b is not equal to 0, then there is no solution, right? But in this case, there's a 0, 0, 0, 0. So it means that ax equal b has a solution where the ax equal b is consistent. Okay, so because there is a solution, so the vector b is in column space of the matrix A. Okay. Okay, so to summarize, the solution of the above example shows that when a system of linear equation is written in the form of the ax equals b, the column space of A is the set of the whole B for which the system has a solution. So if you read through this figure, there is a solution space, something like that. There is, okay, the matrix A transform vector x from the vector B. Okay, so if we define the size of matrix A as a n by n, then this is the R n space, and this is the R m space. Right? So the set of all P for which the system has a solution, like that. So every P here has a mapping here. Okay, and there, this point has a no solution here. Then in this case, this one is the column space. Okay, this is the column space of A. Okay, so column space of A is the set of the whole P for which the system has a solution. Okay, so this is the column space. Okay, then what is the null space? Actually, the column space and null space are different. So, but from next week or from Thursday, we will find out there is a relationship between the column space and null space. But today we just introduced what is a column space and what is a null space. Okay, so what is the null space? Null space of the matrix A is the set of the whole solution of the homogeneous equation Ax equals B, Ax equals 0. Then in this case, we call the null space of A as a null A. So in other words, null A is equal to the set of X that satisfies Ax equals 0, the homogeneous equation. So in other words, the null space A is the set of the homogeneous solution. So what does it mean? Okay, so there is the Rn space, and there is Rm space, and there's a mapping function, matrix A. Then the size of matrix A as the m by n, right? So in this case, the output is the zero vector, right? Comparing to this one, because in here we assume that the arbitrary vector b, but here we only think about the zero vector as an output vector, right? So then there is a possible vector x that satisfy this one. So here, then whole possible x that satisfy ax equals b is called the null space of matrix A. Okay, so this is the definition of the null space. Okay, then null space of the m by m matrix is the subspace of the Rn space. Actually, the column space was the subspace, right? Interestingly, the null space of matrix A also subspace. Then, in other words, equivalently, the set of the all solution of the system Ax equals B, Ax equals 0 of the m homogeneous linear equation and n unknown is the subspace. What does it mean? The matrix A is the m homogeneous linear equation, something like that, and n unknown, right? Then the solution, the set of the whole solution of the system Ax equals B is the subspace. Okay, let's prove. First of all, the zero vector is in null space. Why? Zero vector is equal to zero vector, right? Because the every homogeneous system has a trivial solution as x equals 0, right? So in this case, zero vector is in the null space. Okay, and then to verify the second property, let's take an arbitrary vector u and v in null space A. So in other words, u is equal to 0 and v is equal to 0. Okay. Then by the property of the matrix multiplication, you know what it is. So if you are not, please go back to our previous lecture. Anyway, so A times u plus v is going to be au plus av. Then what was the au? 0. What was the av? 0 from here. Okay, so a 0 plus 0 is 0. So it means that a times u plus v is 0. So u plus v is the null space, right? From here, right? Then let's prove the third property. A times cu is going to be c times au, and because au is 0 here, right? So c times 0 is 0, so it means that cu in the null space, right? So from here, okay? So from this proof, we can say that the null space is the subspace of the Rn space. Okay. So this is the definition of the null space. So far we've talked about what is a subspace and the two representative subspace, the column space and null space, right? Then actually we want to represent each column space or null space or the subspace as a compact form. What I want to do is some problem with the subspace handled best by working with the small finite set of the vector that span the subspace. In other words, if we only have the small finite set of the vector that span the subspace, then we can use this small finite set of the vector instead of using every possible vectors in the subspace, right? So this is the concept of the basis. Okay, so from now on, let's see what it is.